Section 10.3 is regression, and you're going to find that this section is very similar to what we did with correlation, because when we did that linear regression test in 10.2, what we ended up getting were the coefficients that we're going to use to write our regression equation. So basic concepts of regression. The regression equation expresses a relationship between x, called the explanatory variable or predictor variable or independent variable, and y hat, called the response variable or the dependent variable. The typical equation of a straight line is y equals mx plus b, where m is the slope of the line and b is the y-intercept. That's where the line crosses the y-axis. And we're going to express this line in this form: y hat equals b sub naught plus b sub 1 x, where b sub naught is the y-intercept and b sub 1 is the slope. The slope of the line will always be multiplied by the independent variable. Don't worry that the order changes here. This is addition, and in addition you can switch the order of things and still be okay. So a regression equation, given a collection of paired sample data, the regression line, or a line of best fit, or least squares line, is the straight line that best fits the scatter plot of the data. So it's going to take on this form. When we went to our calculator and we scroll up here, they give us this form of the line y equals a plus bx, and a here we got to be this constant 125.4, and b, based on their information, was 1.73. So there's an equation of a line that we can use then for this data for the shoe size and the height. So the population parameter versus the sample statistic. For the y-intercept of a regression equation, beta sub naught. This is a capital beta. That's the population parameter. B sub naught is the sample statistic. Beta sub 1 is the population parameter for the slope or the slant of the linear regression equation, and B sub 1 is the sample statistic. Here's the equation for the line of regression: y equals beta sub naught plus beta sub 1x, and the sample statistic, y hat equals b sub naught plus b sub 1x. So once again, we're using sample statistics to test a claim about a population parameter. We've been doing that with means. We would use x bar as an approximation for the mean. We would use the standard deviation as an estimate for the population parameter for the sample statistic. We did p hat as an estimate for p, the population proportion. So if you see a hat on a variable, then you know that it's coming from a sample, not a population. We have the same requirement, being that the sample of paired data has to be a random sample of quantitative data. Visual examination of the scatter plot must show that our data follow an approximate straight line pattern, and any outliers must be removed if we know that they are collected in error. These are formulas for finding the slope and the y-intercept, but guys, we're not going to worry about the formulas because we have calculators. Let us return then to the example from 10.2. We would like to use the explanatory variable x, the shoe print length, to predict the response variable y, the height of individuals. So here's the list of data that we put into list 4 and list 5. We do the requirement check. It's the same as it was for correlation. And then using technology, we end up with the following output. This is the one that we're going to focus on because this is the technology that we have available. If you're familiar with Excel, you can use the linear regression equation model in Excel to come up with a linear regression equation. Minitab, SPSS, and StatDisk and JUMP are also other statistical software packages that you may see, especially if you go to Baylor. I believe when I was at Baylor, we used JUMP. In grad school, we used SPSS. I think this is the one that used to be available with the book. I'm not familiar with Minitab, but everybody has access to Excel just about nowadays. So you may see these different software results. All of these technologies show that the regression equation can be expressed as 125 plus 1.73x, because that's the linear regression equation we came up with from the calculator. Looking at the output from our calculator, we got 125.4, which we're going to round to 125, and then 1.73 will be the slope. When we plot that line as we did in red here, we can see that that is the line of best fit for these 5 data points. But if you remember from the correlation problem that we did in 10.2, we said there's no linear correlation here between these 5 points. That doesn't stop us from drawing a line of best fit, and that's what that linear regression line is. We can still come up with it even though our p-value indicated there was no linear correlation. It's still a line of best fit. But now the question comes up, how do we use this regression equation for predictions? If there is a correlation, we can plug in a number for x and solve for y using this linear equation to predict values. So if I knew that a guy wore a size 31 shoe and I wanted to figure out how tall he might be, well, then I would go over here and plug in a 31 in place of x and solve for y and see, that they're about 180, maybe 178 centimeters. That's something you could use regression for. Use the regression equation for predictions only if the linear correlation indicates that there is a linear correlation between two variables. If there's not a linear correlation there, then we want to use the regression line for predictions only if the data do not go much beyond the scope of the available data. If we predict too far beyond the data that's available, that's called extrapolation, and it could result in bad predictions. If the regression equation does not appear to be useful for making predictions, the best predicted value then will be the sample mean. Don't plug in a number for x and solve for y in the linear regression equation to approximate y. Use y bar, the average value of the y's. So if the regression equation is not a good model, the best predictive value is y bar, the mean of the y values. This strategy applies only to linear patterns on points of scatter plots. So using the 5 pair of shoe print lengths and the heights to predict the height of a person with a shoe print length of 29 centimeters, the regression line does not fit the points well. That's why we came up with there's no correlation, which means that we need to use the average value to predict y. And that's pretty much all you want to get out of the linear regression. We use the same test, the same stat test for correlation and regression to look and see if there is a correlation by looking at the p-value here. And also we can use the a and the b that come out of the output, plug them into the function here for a linear regression equation. We are done.